giving a general idea about what are the different types of welds and what are the different types of constraints that we may be having in weld inspection. Then I'll come to advancements. The topic that is selected is advancements. So I'll first say that what is advancement in NDE techniques? Why do you need to do the advancements, and what are the advancements that we are basically talking about? Then first briefly I'll share about advancement in a few techniques such as visual testing, magnetic particle testing, eddy current, radiography, XRD, and so on. And then I'll come to most of my talk. I'll be concentrating on advances in ultrasonic techniques, where I'll first touch upon ultrasonic imaging, where even handheld ultrasonic C-scan imaging, which so far mostly people have been doing C-scan imaging in the lab, but I'll show some system where you can even do that in field application. Then most of my talk will go on the phased array ultrasonics, where we have done a lot of studies, and that is one of the advanced ND technique, which is obviously going to rule the future of the ultrasonic technique. Then briefly, I'll show about the time of flight diffraction based technique, which we have developed in our lab also, the equipment. Then guided wave inspection, which we carry out for various applications. Then I'll share about few other advances like non-contact ultrasonic technique. And then one typical example I'll give at the end, where not just the defects of larger dimension, but even the micro cracks also can be characterized using NDT technique, particularly the ultrasonics that I'll be talking about here and summarizing my talk. So just to say a very brief about what is NDE technique. In the NDE techniques, you basically use one form of energy. There are different forms of energy, and most of the energy and most of the physical properties of the materials have been utilized in the field of NDE. So you take any one of energy, like it could be light energy, it could be microwave, it could be X-rays, it could be gamma rays or ultrasound or thermal. So you use some energy in form of wave or particle, and you throw that on the material, and then you try to study the response of the material on that energy that has been put on the material, or you try to see that when the energy goes through the material and you detect it, what are the changes in the energy that has come as it is propagating through the material. And that carries the information about the material. So the signature of the material is hidden in the output of the signal that we get. So essentially, if we see that what are the different steps that is involved in this, we'll start from the first that you, as I said, you need to apply a testing medium or inspection a medium or some form of energy. Then you see that how this the sample or the material has modified or affected the testing medium or testing energy. You detect this change by a suitable detector. Then this conversion of this change, whatever has happened, to a suitable response is done, and that is interpreted in terms of measured response, like either in terms of signal, which mostly people have been doing in terms of like ultrasonic or eddy current or so, in terms of images, like in case of radiography, in terms of some data. Nowadays, most of the signals, images that we talk about is ultimately converted from analog to digital converter, and you have it in terms of the values, the data, and which can be used for go, no-go kind of data as well. So interpretation of the measured response, signal or image or data for decision or quantification. To take a typical example, if we see for X-ray film radiography. So when we talked about the application of a testing inspection medium, here it is the X-ray energy that is being used. Then when we talk about the modification of the testing medium by flaws or the material, it is the flaw in the material, or if you have a high density or low density material in the component, that will modify the intensity of radiation reaching the film, because different differential absorption will be there. And the film which is kept on the opposite side of the sample, that sees the differential X-ray intensity reaching on the film. Then the detection of this change by a suitable detector. So here you have silver bromide emulsion, which is there on the film, which is sensitive to X-rays, which is used as a detector. And then this, whatever detector has seen, and then there will be separation of this silver ions that is fixed by this emulsion record variation in the X-ray intensity, and permanent record is obtained by darkroom processing. And then we interpret the radiograph through variation in the film or optical density. So this gives a very general idea about the different steps which is followed. In principle, if you see any other NDE technique also, the different steps will be more or less similar to this. Maybe it was, in some cases, it may involve before this some kind of sample preparation also, or towards this some kind of image processing also. But in the core, the steps are going to be more or less similar to this. So now here we have just listed out a few NDE techniques which are most commonly used, like visual liquid penetrant testing, magnetic particle, ultrasonics, radiography, eddy current, in situ metallography, X-ray diffraction, acoustic emission, and thermography. Out of all these techniques, if we see there, the two techniques which are highlighted here now, acoustic emission and thermography, these are the techniques which are only dynamic. Dynamic in the sense that, let's take, for example, acoustic emission. Acoustic emission can be utilized when, for example, if you have a big hot sphere, or you have a pressurized gas cylinder or pressurized gas tank. Before you use with the required gas or so, you may do the testing at different pressure level. When you do the pressure testing of the component, at that time you can mount different piezoelectric or acoustic emission sensors at different places. And as a function of pressure, you can try to monitor whether there is any, if there is any dynamic event happening, that is, if there is any crack which is growing, that will give you acoustic emission, and that can be picked up by these sensors. And that can give us a warning that there is a crack which is dynamic, which is live, and which is propagating as we go and increase the pressure level. But if there is no increase in the length of the crack, if there is no dynamic phenomenon that is happening, we will not be receiving any signal from the component. So that is how the acoustic emission works as a dynamic technique. Similarly, let's say thermography. Thermography can be active or passive, but in case of passive, where we talk about normal, just we are picking up the temperature distribution. So a very typical example is that when you touch any electrical switch and you feel that it is warm or it is hot, so that gives you an idea that okay, there is something going wrong. There's been overloading, or there is somewhere some spark, some leakage that is happening. Now, exactly in the same manner, but here we are going to touch it, but without touching, you can simply monitor on a thermographic camera, and that can give you idea about where is the thermal spot. And that can give us an idea about that if something is going wrong there, you will see a thermal spot, and that can be utilized for example, to find out any leakage or any overloading on a electrical switches, or even that can be used for various other applications. Like if there, let's say in a wall, if there is any leakage in water somewhere, and you just monitor the temperature, you will find that wherever the water is leaked, that place there may be a bit of cooling compared to the other location. So without doing any physically any change, you can simply monitor the dynamic event, whatever is happening there. That itself we are trying to pick it up in these two cases. Now, coming to the other type of categories of NDE techniques, you have visual, liquid penetrant, in situ metallography, X-ray diffraction. These are the techniques which give you idea only about the information on the surface. Visual technique, most commonly used, very simple, the cheapest one, because in many of the cases you will be just going and seeing the thing, whether it looks fine, whether there is any corrosion on the surface, any micro crack, any crack, or anything is seen on the surface, any deformation, change of the shape, size, anything is there. Even though it does not involve in general very hi-fi equipments, but it is one of the most widely used technique, and it is a technique which is applied before you go ahead and apply any other technique. Because when you go to the site, when you see a component or structure, the first thing that you try to see is you get the visual impression of that. And then you decide that what is the requirement and which other technique would be most apt, or technique which can be applied on to do more detailed investigation. Then we have here liquid penetrant testing. So liquid penetrant testing is basically one of the technique which is almost applied every time you have a welding done. After the welding, people would try to check with liquid penetrant testing whether there is any crack or so there on the weld or near the weld in the toe region or on the top or so. This is again a cheap technique, not very costly technique. You don't need a lot of money for that, and you don't need a lot of expertise on that. But it gives a lot of information, and in practical, in most of the places, wherever a welding is done, the first and the most important technique which is applied most regularly is the liquid penetrant inspection. Then I've also listed two more surface techniques like in situ metallography and X-ray diffraction. We know about the metallography technique that for doing the metallography investigation, which gives you the microstructure of the sample. Basically, what you do is you take the sample, cut into small pieces, and then you do polishing, etching, and see the microstructure. So that is about the destructive way of doing it. In case of in situ metallography, when we talk about non-destructive manner, you basically take the wheel polishing machine, and then you go to the site on the big component, you do polishing of a small region, and then you do a small etching. So that essentially you're only removing few hundred microns of the material thickness, which does not really affect the serviceability of the component. And you see the microstructure either in situ by using a handheld microscope, or you take replica on cellulose tape or something, which can be analyzed in more detail later on in the lab. Then we have X-ray diffraction technique, which gives basically the idea about the, it can give you idea about the material composition also, but mostly it is used in case of welding to find the residual stress which is present after the welding. Now, this was all about the surface techniques. Now let's go to the subsurface techniques. There are subsurface techniques like magnetic particle testing and eddy current testing. When we use liquid penetrant, it gives us only the idea about the defects which are open to the surface. But if we use magnetic particle testing, of course, it can be utilized only on ferromagnetic material. But when we use this, it can give you idea about the surface open defects as well as the defects which are not open to the surface, or which have got somehow, when you do polishing or some material is covering the opening of the crack on the surface, which will hinder to see the signal or to see the image clearly in liquid penetrant, but in magnetic particle you will still be able to see that. And then the other technique, which is subsurface technique, is eddy current technique, where you apply an alternating current that in a coil, and that coil generates a magnetic field, cycling magnetic field, and that induces current inside the material, eddy current inside the material, on a conductive material. And the depth of the conductive, the eddy current that is generated exponentially drops with the thickness. So you will be essentially able to see only a few hundreds of micron or a couple of millimeters maximum by using eddy current technique on the surface of an electrically conducting material. And that is the reason that mostly eddy current is used for inspection of thin plates or tubes which are not very thick but having long. So the advantage here is that you don't need like a coupling or so that you need in case of ultrasonics, and you don't need to take so many snaps like in case of radiography, but it can give you, it can be a very fast inspection method for inspection of the tubes components or thin sheets or so. Then we come to the volumetric techniques. We have ultrasonics and radiography. These are the only two techniques, which ND techniques, which can give you the idea about defects in the volume of the material. Radiography is something which has been most widely used in the past so far in the history of welding or NDT. If you see, it is a radiography which has been used most widely for almost any radiography, any welding. And the primary reason for that has been that radiography, when you do, it gives you image of the internal of the sample. Mostly it will give you the volumetric defects like porosities or inclusions, so that they can be very clearly revealed in case of radiography. But There are some problems, some limitations with the radiography, and those limitations essentially include that when you use radiography, you use X-rays or gamma rays, which are harmful, radioactive, with respect to the exposure to the radiation. And that is why it cannot be done in the, mostly what people do on sites is that in the daytime when they do welding, and the night time when not many people are there, at that time the radiography is carried out. Radiography gives you very nice image of the internals of the of a weld, and it also gives the idea about the weldmanship also, like whether the welding person has done the welding properly or not, because that will, if the welding is not done properly, it may lead to more amount of like inclusions, or some, if the electrode was not dried up properly, you may have more pores or something. So those information also you can get in the radiography. And the images which are generated can be archived for any future reference, that in future again, if any inspection has to be done, then this can be used as a baseline information. So that is why radiography has been, and it does not require very high amount of expertise of the person to analyze the radiograph, because you see the things very clearly in form of images. And it is very easy to say that, okay, here you have the porosities, here you have the inclusions also. But the limitation that you may have in case of radiography is that when you have some very tight cracks, and if the orientation of the X-ray is not proper, then there are high chances that they may be missed, because you are only talking about the change in the total attenuation or absorption of X-ray by the material along the ray of propagation. So in case a planar defect, which is a tight crack, if it is misoriented, you will be seeing only a few micron loss out of, let's say, 30 millimeter thickness of the sample. And the best, most commonly achieved sensitivity that you get is of the order of around 2T or something. That means 2% of the thickness. So in such cases, chances of missing these fine defects are very much there. Then we come to ultrasonics. In case of ultrasonics, is also one volumetric technique which can be used for detection of defect at much larger depth. And the advantages that you have with ultrasonics, which as compared to, let's say, radiography technique or so, is that you have very large amount of flexibility, which makes you to choose with the expertise. Of course, the expertise required in case of ultrasonics may be slightly, the requirement may be slightly higher as compared to the radiography. But if once you have the expertise, then you get a lot of flexibility here. For example, you can do inspection of concrete structure with very low frequencies of the order of around 50, 60 kilohertz or so. You can do inspection of cast structures, cast metallic structure also, by selecting frequency in the range of around a few hundred kilohertz to about 500 kilohertz or so. You can do inspection of other force components. Maybe you can slightly go on increasing the frequency, because higher the frequency, more is the attenuation in the material. So finer is the structure, you can grain size, and thinner is the structure, you can go to higher and higher frequencies. So you have the possibility of changing the, selecting your suitable frequency, like what you would have selected otherwise in case of radiography by the energy of the beam. Here you can select with the frequency. And higher the frequency, better is the resolution or sensitivity that you will be able to achieve in the given material. Not just that, by selecting suitable wave mode that you are going to use, you can select either the surface wave, which can give you information only about the surface, bulk wave like longitudinal or shear wave or something which can give you idea about the bulk of the material, or you can use guided wave, which can give you idea about some component which is having thickness less than about a wavelength, and it will give you, it can propagate for a very long distance. We have used for some steam generator tubes or so, where we can get information up to about some 30 or 40 meter distances as well, by inspecting from one particular probe position. So that was about the characteristics of a few NDE techniques. Can somebody just confirm that I'm audible and everything is going fine?
Yes, sir.
Okay.
So fine.
Good.
Yes, sir.
So now let's go. Thank you. So now, because we are confining on this talk to the welds, I would just like to show a few cases, like the different types of welds that we may have to inspect when we do in NDT. So I have selected one example from, let's say this is a nuclear fuel bundle of a pressurized heavy water reactor, where we have the uranium oxide fuels inside this zirconium based alloy clad tube. And this tube is, after filling the fuel inside, at the end we have a end cap weld. So this is like an end cap here, and this is a weld, small weld here. So the weld will look something like this, which is done with the resistance welding. So in this case, the thickness is about 0.4 millimeters, so around 400 micron or so. In the same thing, after these individual pins are made, then it is joined together using a plate kind of thing here, which is called end plate. And this end plate is welded with this, with the spot weld. Like spot weld is very common even in case of a lot of in automotive sectors. You will see so many places the spot welds are there. So here, in this case, the weld is inclined at an angle, so we need to do angle beam inspection also. In this case, the weld is parallel to the top surface, so you need to do normal beam inspection also. And here, the size is about 2 millimeters also. In another example, a few of these examples I'll show as I go ahead in my talk. And another example is taken from narrow gap dissimilar weld in rotor of advanced ultra supercritical power plant, where the total thickness of the component is about 1 meter, 800 millimeter to 1 meter, and thickness of the weld here is about 250 millimeter or so. So here, starting from 400 micron here that I was talking about to about 250 millimeter or so could be the thickness of the weld, and we need to inspect this with appropriate selection of the technique and the frequency and the technique, and to ensure that we are able to detect the defects which would otherwise lead to problem during the service of the component. And these were a few different types of, which were basically some welding things, three different types I've shown here. Then the fourth one shown here is friction stir weld, where mostly you try to use it for joining different types of materials which are otherwise difficult to be welded together by conventional fusion-based technique. Like in this case, we have aluminum and stainless steel, and there here the friction stir head is there, which is moving and generating. Finally, this is an X-ray image of this friction stir welded sample. Now, that was with respect to different types of weld. Again, when we go to do the inspection of these components in service, then you may have different constraints for doing the inspection. I'll show you a few examples. So one, this is in the case of a boiling water reactor, nuclear reactor at Tarapur, where this is the photograph of the reactor taken from the top when the fuel elements are removed from here. And then this is the pressure vessel that you need to inspect. When you need to do the inspection of the pressure vessel, this whole water is active, and then you have to use a very long rod or guide kind of thing, where at the end you have a scanner like this, and the scanner will have different types of ultrasonic transducers, normal beam, angle beam transducer, so which will be used for scanning the welds in this, and the data is collected. And then we have even developed our own software for doing the detailed analysis of the data which is acquired here, to find out whether there is any defect inside the material or not. And if there is a defect, then more detailed analysis is done, that if this is the defect which is present in the material, then the fitness for purpose is analyzed, whether the component is fit for the for further service with this kind of defect present in the component or not. So similarly, this is another example that giving where for the prototype fast breeder reactor, in which is an advanced stage of commissioning at Kalpakam, where this is a sodium field fast breeder reactor. So inside it's like a big bucket. Inside everything is filled with hot sodium, which during operation it will be about 500 degrees centigrade, and during shutdown 550 degrees centigrade, and during shutdown it will be about 150 degrees centigrade or so. There's a gap between two vessels here of about some 250 to 300 millimeter gap. And this height is about a few meters, about 10 or so. Now, if you want to do the inspection of the welds which are here, we need to send a gadget or a robotic device which will go inside, and then it will do the scanning of the surface. And from there, we will try to inspect different welds as if you are doing with manually with your hand when you are sitting just next to the weld joint. That is fine because you are able to, in the probe, if it is able to reach the location where you are trying to do the inspection. But there could be some cases where your probe cannot reach the location which you want to do the inspection. For example, one typical case from here I've taken, where this is the main vessel here, and then there is a plate connected to this, and there is a weld over here. Now we need to inspect this weld also, which you cannot directly access because everything is closed inside this. So the only access is from the bottom. And from here, the probe cannot go here, but the wave can travel. So this is where we try to use the guided wave, where the sound wave is sent from here, the guided wave goes along the plate, and if there is any defect in this weld, that will reflect back and give us a signal. I will try to show in later slide, because once you go to such complicated structures and complicated inspection techniques, then you need to do suitable simulation to confirm whether whatever you are doing is that correct, what is the sensitivity that you will be able to achieve. And the simulation is done in 2-3 different ways. One is you do the finite element simulation of the whole scenario, and the other thing is you try to simulate as close to this as possible for the experimental condition, and also do the experimental simulation of this entire thing before you can really take it up and do on the actual component. This similar guided wave based technique is also used for any place where you have only one location for the transducer to bring in contact with the component, but you want to do inspection of the entire length of the sample. Like in this case, let's say you have large pipes which are underground pipes are there, and you want to do the inspection of this pipe. You have got access only to the top location. You can send the sound wave which can go as a guided mode on guided by the thickness of the material. It will go and come back. If there is any defect, there is any corrosion at the bottom, you will see the signal because of that. You can keep it here. Only one location is exposed. You have dig a hole there, and then you are able to mount the transducer. Then you don't need to expose the entire length of the pipe to do the inspection. From here itself, the sound wave can travel as a guided mode and for a large distance, and it can come back. If there is any defect, you will get a signature, and then you can do the analysis of that. Wherever you find a defect, then only at that location digging can be done, and then more detailed analysis can be done there. And because we are talking about only welds, so just to give a few examples about the different types of the defects that you can expect in a weld, starting from maybe if the bottom is not filled properly, so you may have incomplete penetration. You may have a lack of sidewall fusion, where the weld material has not got fused properly with the parent metal here. You may have the porosities. The white ones are shown where the material is missing, and the dark one, this is the slag or the high density material you may have here. Then you may have toe cracks kind of thing just at the toe of the weld, or different types of cracks may be there in different types of material, depending upon the composition of the material, depending upon the welding that you are doing, which are prone to different types of defects in the material. Then you may also have, like when the welding is done, of course, there is a huge amount of heat that is given here, and you have the weld metal, which is liquid, then gets solidified, then change of the volume is there, and then you may have change in the microstructure also, like phase transformation. All this may lead to some amount of distortion in the material or different extent of residual stress in the material. And this residual stress can lead to any kind of fatigue damage or something, fatigue crack initiation, which basically depends upon if on the surface you have tensile stress that can lead to, or that can help in generating more fatigue cracks on the surface, or you can have like stress corrosion crack kind of thing, which will happen more if you have a tensile stress in the sample. So sometimes it is also important to measure the residual stresses, which I'll show as X-ray diffraction, but many places X-ray diffraction cannot be taken to the surface. Then you have other techniques like ultrasonic velocity measurement chain that can be used for measuring the stress in the sample, or you can have magnetic Barkhausen emission, which can be utilized only on the ferromagnetic material, but that can also give you idea about the stress that is present in the material. Now, with this brief idea about the NDT, the weld, and all, now we can see that why, when we talk about advances, why do we need to go for advances, and what are the advances which really we do? So, for example, why do we need advances? We need advances in ND techniques to improve the sensitivity and signal to noise ratio. So what is done in case of, like, if you say in case of ultrasonics, you try to focus the beam so that you improve the signal noise ratio, you improve the sensitivity, you improve the resolution. In case of eddy current, you may try to go for high sensitive sensors like giant magnetoresistance sensors, GMR sensors also, which can pick up very small field. In case of now, why do we want to go for advances? The other reason could be we don't really want to get only the point information, because that makes it difficult to visualize that how exactly if there is a defect, what is the distribution, and what is the shape and size of the defect, better characterization. So we need to go from point information to imaging. So to go from point information to imaging, the possibilities are that you can use multiple probes. So, or you can use array probes, like which I'll be discussing more in detail in the phased array ultrasonics. You can do scanning with a single element transducer itself, but scanning can be done. And then all the data that you acquire, it has to be suitably represented or presented for better visualization of the defect signature. So you need to have a good software development which can give you better visualization of the defects. Then you do not want always the NDT inspectors, all the NDT inspectors, to be highly professional and knowledgeable to understand each and every signal also. What you may prefer is that the technique itself should be developed in such a way that even somebody who is not having very high expertise, he should be able to directly visualize and see that what is the kind of defect that is there in the material. But of course, then the development part has to be done by an expert in the field, and the expert should also be able to transform the basic data that you get by the transducers to a form of image or a visual representation of the entire thing. Basically, you would like from the signal, which is a qualitative signal, to go to a quantitative image, which can be directly, clearly understood by even a non-expert in the field. Then you would like to avoid manual scanning. To avoid the manual scanning, the advances could be from the automated scanners, robotic devices, electronic scanning, which is done in the phased array ultrasonics also. Then in many cases, something which is inaccessible component, like just now I showed one or two examples of the pipes which are buried, or the components or the welds which are directly not accessible. For such cases, we can use remote vehicle, or you can, if the vehicle also cannot go, we can use the guided wave also. Then we would like to do not just the defect detection, but comprehensive evaluation. That means if you have some major or large crack, or you have some micro cracks which is present in the material, or even you would like to also measure if the stress is there in the component. So basically, to go from the conventional, what people used to talk about, non-destructive testing, to non-destructive evaluation, which gives you not just about the defect, but also tells about what is the microstructure, what is the stress present there, so that more detail and the real fitness for purpose calculation can be done. Because from the microstructure, getting the information of microstructure from NDE, you can also get to know about what could be the fracture toughness, and by applying that, what is the stress present there, that can give that what is the stress at which the component can operate with the defect that is present, which you have found using the NDT technique. Essentially, all these advances we are trying to do to go from something what in the past people used to say that it is not possible, to make it possible, basically to push the limits of all the techniques. That is what we are trying to do as we are trying to go to the advanced techniques also. And this is essentially achieved by improved electronics, computer, software visualizations also, development of new and more sensitive sensors, defining different algorithms which can convert the raw signals to direct visualization, the quantitative visualization, or artificial neural network also, which can help us in selecting the defective and non-defective things. But what I would also like to mention here is that whenever we say we are going to advanced techniques in any of these fields, essentially we should keep in our mind that the basic physics of the technique does not change. It remains exactly the same. Whether we talk about the conventional radiography, where it's the film radiography, you have it works basically based on the absorption of the X-rays by the material or the component, the differential absorption. The same thing happens whether you talk about the film radiography, you talk about digital radiography, or even you talk about the computer tomography. Everywhere the basic physics and the interaction remains the same. It is only the way you are trying to analyze, to make it fast, to represent the information that you have got in a suitable manner so that it can be analyzed in much better way. So the basic physics remain, and same thing is valid when we are talking about the conventional ultrasonic testing, or you talk about the most advanced phased array ultrasonic technique. When I say most advanced, it is not just the conventional phased array. Even in the phased array, also the most advanced methods that we talk about. Everywhere the basic physics will remain the same. Now, a few quick things to show the advancements in different techniques. Like here I'm showing about the visual. Conventional visual, you just see on the top from outside the surface. Whereas when you want to go into more detail, other people would say that, okay, inside the pipe, we do not know what is there. But now you can use techniques like videoscopy also, where this is just a photograph of a videoscope that we have in our lab. So you can use a videoscope where the diameter of the tip is only about 4 millimeter or something. So that means in a tube of about 4 millimeter or larger dia, you can push this. It can go up to about 3-4 meters distances, and you can see inside the images very clearly. Fine. This also is not something very new. People have done even 10-15 years ago. Also, it was there. Now then, once you start doing something, then people always want more and more. So when you want more and more, that means first it was only to see what is the inside. Now one would say that this is not sufficient. Maybe can we see better what is there on the surface? So one could use even the side viewing camera in that. And then you can get better focused image of the side surfaces. This also is not sufficient. People want to know that if I find there is something over there, what is the size of this? To measure the size of this, we know that God has given us 2 eyes. And the 2 eyes are there basically because when you have 2 eyes, you can focus on something, and then you can get an idea about the depth of the object. So by the angle that it forms on a given object, you can get an idea about that, what is the depth of the object. And when you have similarly 2 cameras here, which are at a fixed distance and slightly inclined, and when the image is captured by these 2 cameras for the same region, you should be able to get an idea about what is the size which is there, what is the depth at which you are doing the measurement, and also what is the size of any object or if any defect or anything is there, you should be able to do the quantitative measurement of that also. So that's what is the advancement when we talk from the conventional visual inspection to the recent advanced techniques. Then for the magnetic particle testing, we know you can apply that on any ferromagnetic material. You apply magnetic field using a yoke or current, and then whenever there is a hindrance to the magnetic field lines, then those magnetic field gets leaked out in the vicinity, and basically it gives you tiny magnets which are forming there. And you can sprinkle iron powders, and that they will get aligned along this crack or so. That is conventional magnetic particle testing. But the most advanced versions, you can even go with the emulsified things where you can see the better images, or even further advancements. You can, rather than doing this sprinkling the powder, you can have a small sensor, which can be Hall probe or GMR sensors also, which can pick up very tiny fields, and that helps in detecting the surface open or the subsurface defects. And you can very effectively use it for without sprinkling. You can automate this very effectively, and you can map on a larger area. In fact, this kind of magnetic flux leakage technique can be used where we cannot go and do the inspection to sprinkle the powder and all. You have the magnetizing unit, you have the sensor which is receiving the signal if there is any stray field leaked out. And this can be used for like large pipe inspection gadgets, which are used to do inspection of long oil pipelines or so. In all those cases, this many magnetic flux leakage sensors are there, and the whole pig, that is pipe inspection gadget, can be inserted, put inside the pipe at one place. With the oil flow, it can go to larger distances, and then you can pick up along the length. The data is acquired, and then at the end of that, it is taken out, and in that you can see that where all any defect was present in the pipeline. And this is just to show that when you do the mapping for a small hole, you can get a distribution like this. And this is just the distribution, but then if you apply properly, like maybe one slide I'll show for the eddy current, that this kind of signal you get with the raw data, which can be improved drastically using artificial neural networks or by suitable processing to get exact the kind of defect that is there, rather than getting the total footprint of the probe also here. So it can be deconvoluted to find out the exact type of the defect that is present inside the material. Now, to go for the advances in the eddy current testing, you can have, when we talk about the advances here, we are trying to do advances in different scope of that. Like in the eddy current testing, when you have sensors, you're trying to improve the sensor so that you get more and more sensitive, better sensitivity of the sensor. It can pick up the small leakage field or small magnetic field. Then you have advancement in the instruments, which can earlier, which was only working, giving you some poor signal noise ratio. Now you can get much higher signal noise ratio. You can have instrument which can work for a multi-frequency range to give you the idea about the variation in the material at different layers, because the higher frequency will be confined to the top layer, and low frequency will give you more information about up to larger depth also. So the instrument wise, you can have a multi-frequency ND technique, you can have pulse eddy current technique. So the development or the advancement in the instrument is there. Then you can have automation where the sensors or the probes can be automated for doing the large pipe inspections or inspection of stream generator tubes or something. Then the data that you acquire, you will try to do the suitable imaging of that. And this various image processing algorithms could be used to deconvolute the real information or the defect type that is present in the component, not just getting the raw data, which gives you the idea about the convoluted information about the defect as well as the footprint of the probe. So you can try to get the real information about the defect itself. And then we always try to do with the finite element simulation or the other means of modeling, doing the simulation of the defects or the interaction of the eddy current in the material, so that it can give that, it gives us that what do we expect before we even go to do the inspection. And it helps us also to design our sensors to get the best sensitivity and the response that we need from the component. So just to show one or two typical examples here, with the eddy current probe, you can, once you go across the floor, you get the X and Y components of this in terms of the signal. But then if you do mapping with the raster fashion using the same probe, then you can get the detailed idea about that what is the 2D distribution of the defect here, or the whole type of defects or something here. But this, again, this still gives you the total, only the information about along with the defect and also the footprint of the probe. But then it can be utilized, like this is what you're getting here. But then by suitably incorporating with artificial neural network, so you can try to get into not just the raw signal, which gives you the footprint of the probe as well. You can really get the information about the defects, the length or the width of the defects, also very localized information, right, of the detail about the defect. So this was just to show again that if you about the probe or the sensor, that when you want to pick up, as I said, that the eddy current is mostly the subsurface technique, where only up to about some depth of the material you can get an information. But if you use a sensor which is very highly sensitive for a small field also, then we should be able to even pick up the information that is coming from deep inside the material, like almost beyond, this defect is beyond about 5-6 millimeter, which is much deeper for the case of eddy current. And you're still able to very clearly resolve the defects which are present here. In case of radiography, the advancements when we talk about from film radiography, you have gone to digital radiography, where you get instantaneous result of the radiography image. And then, of course, as you get the just radiography image, that is not sufficient, because you have differential, if you have different types of sample geometry, you may see the somewhere the exposure may be less, somewhere the exposure may be more. So then suitable corrections are required to be incorporated here to, that is digital signal processing is required to be done, digital image processing is required to be done, which enhances the image qualities, as can be seen, some little bit can be seen here with the improved one as compared to the raw. And then these images can be stacked together by using computer tomography algorithm, where in our lab colleagues have developed the tomography algorithm, and then we should be able to reconstruct the image like this for the pipe. You should be able to reconstruct and get the defects, exact weld, the concavity, or any other issue that is there in the weld, or even you can zoom into that to find out anywhere any small micro crack, like here the cracks can be seen in different slices that is generated. This is about showing the residual stress measurement. Residual stress measurement with XRD, X-ray diffraction, is done with by using Bragg's law, where n lambda is equal to 2d sine theta, and then you try to get the peak, X-ray diffraction peak, and the peak shifts when you have tensile stress or when you have the compressive stress, because when you have stress in the material, that gives you the stress will change the interplanar spacing, and the change in interplanar spacing will change the d, where n lambda is equal to 2d sine theta. So when d increases, theta becomes smaller. So by doing the XRD measurement, one can get the residual stress measurement. That was fine, that people have been carrying out for quite many years. Now the advantages that you have is rather than just having one single value that you get, you have sensors which can, photosensitive devices which can give you at one probe location itself more amount of data, more theta angle data can be acquired, so that the measurement which was taking earlier maybe once on one weld, if you want to get few measurements across in the heat affected zone or away from that, if that was taking earlier a few hours to complete measurement on one pad, it can take a few minutes, maybe around 10 to 15 minutes. You can complete the entire, get the map of the residual stress on the entire weld region, and that can be easily generated, and it gives the idea about the distribution of the residual stress along the whole weld surface, and much faster way, and much more information in form of image than as earlier in just one point information we used to get. So now, okay, now whether the organizers can tell me how much more time do I have. Based on that, I will go ahead for the next part.
Sir, I think you can continue till 4:30.
Till 4:30. Okay.
Yes, sir.
I think I started around 2:30 and it went up on 40 minutes I spent. Fine, I'll take maybe around about maybe 4 o'clock. I'll try to see, and then maybe then we can, or maybe
Question
fine now
answers.
if anybody.
Then we can follow with sir question answer session, sir.
Exactly. Or right now, if anybody has any general question, we can see, because now onwards I'll go into only the ultrasonic testing. So if anybody has any particular question or something, right now maybe we can take one or two, and then I'll start about the ultrasonic part. Okay.
I think
so.
so,
If
sir,
nothing,
you can continue. Yes, sir.
sure. So I'm not talking about more detail about the very basic of ultrasonics. Did you, in the yesterday's lecture, did you already have something about the basic of ultrasonics? Can somebody else confirm that in the yesterday lectures, whatever you had, did you have anything about the basic of NDT technique, basic of ultrasonic technique or so?
Yes, sir.
Okay, fine. Then maybe, and some B scan, C scan or something was covered in yesterday's lectures?
No, sir. This A scan, B scan was not covered. Only the basics of ultrasonics was covered, sir.
Okay, fine.
Pulse echo method,
Okay,
critical angles.
Fine. Okay, good. So fine. So then I will, in this slide, I'll spend some time to first tell you about the image types that we talk about, because in the later slides, you will see many of these B-scan images. So it is better that you get acquainted with what I'll be talking about. So the first thing, whatever said that yesterday, you have been, some parts have been covered about the pulse echo technique. So like here you can see I have got a transducer, and this is a typical of one sample, which is a rectangular block, and then there is a cutout from here, which we can assume to be, for the time being, like a defect or so. When you keep a transducer here and send a pulse to that, the sound wave, okay, this is just to show that when we will do the complete raster scanning on this, when you have the transducer here and you send a pulse, the sound wave goes and comes back. The sound wave goes and comes back, and because of that, you get a pulse in the A scan signal. So the raw data, raw image that you see, where I have just rotated this, in most of the time on the screen, you will see this, the rotated otherwise, where the vertical axis will be essentially shown, the time of flight will be given on the x-axis, and the amplitude will be shown on the y-axis. And so on the x-axis, it will go straight, and then you will get some signal over here, like in this case, and this is the backward echo signal that you have got. And the time taken for the sound to come back here depends simply upon the sound wave velocity in the material and the thickness. If the thickness, let's say, is T, sound wave goes and comes back, so total time travel is 2T. And the sound wave velocity, let's say, for steel, it is around 6,000 meter per second. So 6 mm per microsecond or something. So let's say it is 2T is millimeters is the thickness going and coming. So 2T divided by 6 will give you the time of flight. So if the thickness of the sample was, let's say, 6 millimeter, so you will get 2 into 6, so 12 divided by 6. So 2 microsecond it will take. From here to here, the time travel will be about 2 microsecond or so. With in most of the digital ultrasonic equipment that you see, normally it works at around, let's say, 50 mega sample per second, 50 megahertz sampling rate, or 100 megahertz sampling rate or so. So that means you will have around 0.1 10 nanosecond. So 0.01 microsecond is the accuracy. So out of 2000 nanosecond, 2 microsecond is 2000 nanosecond. Out of 2000 nanosecond, 10 nanosecond is your accuracy in the measurement, sampling rate. So that means with 1/200th time, you are able to get, with that accuracy, you can measure the thickness or the location of a defect. So that means if you're talking about 20 millimeter, you can do the thickness measurement with about 0.1 millimeter or something. So that is the accuracy with which you can measure the thickness, or that is the accuracy with which you can identify what is the depth of a defect from where you're getting the signal. So this signal, what you see on the screen of a ultrasonic equipment, of course rotated by 190 degree, this one, that is what is called as A scan, amplitude scan or A scan, simple. Now you move the transducer on the top surface. So for this particular place, let's say this is the B scan image. In the B scan image, what we basically do is, whatever you are getting information here, the same information you are trying to put along a vertical line here, and the amplitude of this is converted to a color scale. So if you see here for this vertical line, these amplitudes are converted to that positive side is converted to maybe more red or so, and the negative side is converted to blue, and in between the zero is slightly reddish or very light color image also. And this whole thing is having very low amplitude. Now again, when the second signal is coming here, this is again showing us with slightly higher different color, so that you are able to see this much information is coming from one A scan which is generated here. Now let us move the transducer to the other place. Again, you are getting the reflection from the same depth, so the same A scan signal and the same B scan location. Now the probe has come to a place where the thickness is reduced, or you can assume that there was a defect here. So the time taken is reduced. By measuring the time taken now, you can even calculate that what is the depth at which you have the defect. And the same thing if you try to put in the B scan image, now corresponding to this does not change. So you are seeing the same thing. Earlier we were seeing the echo here at this depth. So here the amplitude was shown. Now the same thing is coming at less depth. So you are seeing the representation of this A scan signal as amplitude here in one color scale. Signature is coming here. Now you move. Now this, so far whatever information you have got here, that is about one line that we are scanning here. Now for the same line, let us say for every point of the probe, if we give in this image 1 pixel is corresponding to 1 point here. So, and then we are trying to just show, we can show that the maximum amplitude that we get within this A scan, or we can say that what is the time, or where we get the maximum amplitude. Let us say when it was here, we were getting the maximum amplitude at D2 depth, which we are representing as a green color image here. Then when we came to this particular place, it came at less time. We are representing, because this is just, this graph is, image is just shown again as a color plot to show in terms of depth of the defect at which you are getting the maximum amplitude. So here the maximum amplitude came at much less depth, so that is represented as a yellow color. Now we just go on moving the probe at different places. Now we have scanned one line. So we have got one cross-section information we have seen already, and that cross-section information is represented here like a B scan image. So the B scan image is basically the cross-section, it gives you basically the cross-section of the sample, that information. Of course, here it has been very simplified that you get exact perfect, like the way the sample is here, you get it like this, but there will be some amount of divergence and all the things that to some part I can cover later. But to see a very basic thing, what you can see here is that a B scan gives you the cross section of the sample where you have moved your transducer from one location to the other location. Now, corresponding to all this information that you have got here, if you forget about only the starting signal, which is coming always the initial ringing, from here to here, whichever location you get the maximum amplitude, that is converted here in the time of flight is converted to the color here. So this place, it came at less time of flight, so it is shown in yellow. And here it is coming at larger time of flight, so it is converted to green. So this one line here is giving us information about one line of the top. This whole image here gives information about whole cross section. So B scan will keep giving, like now when we scan the next lines as we go here. Again, when we do here, so you can see how the B scan is getting generated and how the C scan is getting generated. Okay, so every time you scan the sample, at the end you do not have any that cut part is not there. You are again getting the full thickness. So here in the C scan, you're getting everywhere the signal is coming at the same depth, and the B scan also you're seeing signal coming at the same depth here. So okay, so now the scan is complete. So what you're getting is individual B scan informations is what you are seeing in the individual cross-section information you are getting in individual B scans, and all B scan put together, you are getting information which gives you about the top view of the, like what you get in radiography, something similar to that. That information, what you're seeing, is coming in the C scan image. And this is just one image which is shown for old 1 rupee coin, which is the bottom one gives the photograph from the back surface and the head and the tail. But then here, these are the images which we had generated a long time ago, about 15-20 years ago, on for this coin using ultrasonic C-scan imaging. So basically, we have taken a probe, put everything inside water, and a focus probe is taken. And here you can see that wherever you have the flat surface, that gives us higher amplitude reflection, and it is shown here as white or bright. And wherever you have the curved surface where the sound beam is going and getting reflected in some other direction, there is a drop in the amplitude, and we are getting dark line here. So by just using the amplitude of the signal that you hear, in this example, I was talking about the time of flight based C-scan, but this is amplitude based C-scan, where just by monitoring the amplitude of the A-scan signal that you're seeing at each and every point, you can generate the entire C-scan image of the specimen. What I showed here is only the top surface, but this can always be done from further within the sample information also. And this is how we do normally. This is our C-scan tank, which is filled with water. And then, because yesterday, if you had a little bit of about ultrasonics, you would know that in ultrasonics, we always need to have a couplant, which is placed between the transducer and the sample. What you would have seen, like for medical ultrasound, when somebody has seen, what they do is they have a transducer. They before putting on the skin, they put a gel, and the gel acts as couplant to remove air gap between the transducer and the body. Because in presence of the air gap, the total energy will get reflected back to the transducer, and the energy will not go inside the sample. And that is why when we want to do the C-scan imaging, we fill the tank with water, which acts as a couplant, and you have a transducer which can be there like as a lens. You can have a focus transducer, like this shows a typical transducer that we have. On top, there is a lens kind of thing which focuses the beam to a small size. And as most of us in our childhood, we would have used a lens, and in the sunlight, we could take the lens and then try to burn the paper. So basically, we try to, whatever parallel beams are coming, we are trying to focus at a small point. And that increases the intensity of the beam, and that also increases the resolution. So both this, we get the advantage when we use in the immersion C-scan imaging, using a focus probe. And with that, this is one sample where we had a lot of inclusions inside, and we are able to map all those inclusions. This is a bridge joint where you had titanium and aluminum, and at the interface, some defects were generated. And when from the top, it is inspected, and then there's different slices of C-scan we can generate corresponding to different depths. And all these are merged together to generate a 3D image of the sample, where it gives very clearly that these are the locations where we have defects, and here we get the back echo. Here we have defect, we get the back echo. Again, here we have defect, back echo, and the defects. So that gives very clear idea about the internal of the image by stacking different C-scan images for different slices and generating the 3D image of the internal of the sample. So what I showed in the previous slide was that we use a tank, water tank, in which the sample is kept, but of course you cannot bring a big component and keep inside the tank. So for that, we have a handheld C-scan system. A handheld C-scan system is something like you have this one, you have a scanning mechanism here. This part is filled with water, And you have a focus probe, which is here, and it rotates like this. The red one that you see here is the focus probe, or the beam from the focus probe, ultrasonic beam from the focus probe, which is focused on the sample, and the spirally it is moving, covering about, let's say, about 10 millimeter width and about 15 millimeter, 8 to 10 millimeter width and about 15 millimeter or so in the length. And it is able to focus the beam to about 200 micron size or so in the sample. And then the surface here inside filled with water, and the surface is like a rubber kind of material which has got similar acoustic impedance of that of water. So it does not let the water go out. And using a coupling material, you can couple on the top of the sample, and you can couple this probe. And then just press the button, it starts rotating, and you get the data from the sample. And that data, first you will get something like this, because it is rotating in a circular fashion or a helical fashion. And then this can be suitably represented to get the exact C-scan image of the sample, where we have every step here with about 0.2 or 0.3 millimeter step size or so. And this entire step can be generated here in one go. So this this was the equipment which we had procured, but then the data we are importing and developing our own software to generate the images here, and then from the images to generate the thickness profile, or the frequency content, or the amplitude profile, and everything. So one thing is to get the data, do proper scanning, get the data, and then represent the data properly to extract the information that we want from the sample, and then you get an image of for about 20 by 10 millimeter in about 15 seconds. And this can be taken to any field, and the C-scan imaging can be done in the field as well. And the same equipment was used for one typical example I'll give, where here you have, to start with itself, when I was talking about different types of weld, this is for the end plate weld on the fuel pins of pressurized heavy water reactor. So here from the top, you apply some pressure and the current, and this is the place where the weld nugget has formed. And to find out whether the weld has formed properly or not, earlier there was no technique. It was only that a few sample welds were made, and then you used to use a wrench to break it, and then find out that whether what is the stress or the force required to bend to break this weld. And that was giving us idea, that was giving people idea about that whether the weld, the parameter which is being followed is correct or not. But of course, this could not be applied directly on the final samples. But here, if you use the same probe that I showed earlier for getting the C-scan image, you put, this is what is the C-scan, handheld C-scan system filled with water, and here you have the rubber membrane, and this is the top surface. Sound wave goes. If there is a good weld, sound wave will not stop here, it will go to the bottom and get reflected from here. And if there is a debond here, then the sound wave will get reflected from the this interface itself. And if you take this plate and generate the C-scan, what you see here is, in this cases, you get reflection from the interface, like this here. In this place, you get again reflection from this plate itself, high amplitude reflection here. Near this area, the sound beam goes and goes in some other direction. It does not come back. But in the center, you get reflected or diffracted signal from here, and you see again the high amplitude. Red is the high amplitude, and blue is low amplitude or so. So in the center, you see if there is a loss of this, you would say that there is this plate is not bonded properly with the end plug, and because of that, the signal is getting reflected from the surface itself. So continuously from here to here, you will be getting only the high amplitude signal. And this just shows the B-scan image, where at this particular depth, we can see that here the thickness is less, but this place thickness is more. So you can see here the plate reflection thickness is less, but in the center, when the weld is good, the thickness is more. And that by doing this, you can exactly characterize where the how the defect is there and not there. So like in case of defective case or in a plate somewhere here, you see multiple back oligos like this. Whereas if you go to exactly the center, the time taken is more, so you get the time of the signal comes at larger depth. And that can give you very clear idea about whether the bond is proper or not. And then we could even generate a good correlation by doing measurement on various samples, which were used with the torque meter to find out exactly the torque required to fail the weld and the area that we get the mapping from here. And there was an excellent correlation between the two, as showing that now we can just use this mapping to find out what would be the strength of the weld which has been made. Now, for all these examples that I showed here, we need, when we want to, like as I said, we are able to get 200 micron resolution or something. This kind of resolution you can only achieve if you are focusing the beam. And the beam focusing, when we do, as I said that we are doing it in immersion case. And the reason was were two. One, water acts as a couplant. And the second is that in case of immersion, we can use a probe which has got a lens on the top surface here. And the lens will be a concave surface. With a concave surface, you cannot put this in contact with the sample. Because if you want to put in contact, direct contact with the sample, only the rim will be in contact and the rest of the central region will not be in contact. Whereas if the entire thing is immersed in water, then the water acts as a couplant and we can get nice focusing of the beam happening on the surface or wherever it is required. So that means if we are doing inspection on in immersion, we can get very nicely focused image. But what do we do when we want to do inspection in the contact mode? Because most of the ultrasonic inspection of the components, when we do, it is done in the contact mode only. And that you cannot focus using a conventional single element, mono element transducer that we use here. So for such cases, phased array ultrasonics is something which becomes very handy. If we just try to compare the conventional and the phased array ultrasonic technique, I will go into more detail later, but just to compare first, in case of conventional ultrasonics, you use a mono element transducer. That means you have a single element. When you use a normal beam, the sound beam is going here with each and every small spot on the transducer. They act as individual transmitters, and small waves get emanated from there. And all these small waves, they interfere constructively and destructively within this near field zone where it is shown as beam width is reducing. And at somewhere around this point, by this point, it has formed like a wave. It is something like a typical example when you can say you take many tiny pebbles and throw in water. You will see at every pebble that drops on the water, you will have small wave generating there. But very soon you will see all these waves will interfere with each other. And at the end, you will have one big wave which will be propagating in the water. And that is what exactly happening in case of the transducer, where you have every point acting as a transmitter, but beyond a certain point, that is about the near field, it starts propagating like a one wave front, which is diverging, and then slowly the amplitude goes on decreasing with the divergence. When you want to use this for weld inspection, because the weld is on the right side, when you want to use the weld inspection here, you can't use the normal beam. You have to send the beam at an angle. When you want to send the beam at an angle, then you need to put on top of a wedge. And then, as just now I was told that yes, yesterday lecture you had Snell's law covered, so which tells you about sin I by sin r is equal to V1 by V2. So incidence angle and refracted angle, the signs of that ratio is given by the velocity in the first medium and the second medium. So with that, you can calculate that if you want to send an angle at a particular R refracted angle, then what should be the incidence angle depending upon the material that you're using for the transmitter. So in this case, basically, it is only the mono element in this case here also and mono element here also. And the problems of the mono elements that you can see in the conventional ultrasonic testing is that the beam is continuously diverging. When the beam is continuously diverging, you have slow continuously going on reduction in the sensitivity or the amplitude of the signal. Then beam is diverging, so it's a large beam, so with a very broad nib of a pen, you can only write very big words. If you want to write fine small words with fine lines, you need to have fine focus tip. Similarly, so which you are not able to achieve here with the focus beam, because you can't focus the beam in case of the contact transducer, and you don't have any option of beam control. If you want to scan from here to here, you need to move your transducer from this place to this place. Similarly, when you want to inspect the full depth of the weld using angle beam, you need to move your transducer from somewhere this point, which covers the rightmost, to the leftmost side where the beam can hit the bottom and go to the top. That means what we call as one skip. So slightly larger than one skip distance you may have to cover. But in case of phased array, basically the difference is, in case of phased array, you have here you have one element, here you have many elements. Many elements, like you can have something like 64 elements or 128 elements or something inside one probe, where each and every elements are separately connected through cable through the probe to the equipment, and you can control the firing of each and every element. So if you want, you can fire only the 10th element or the 20th element or the 30th element, and you can receive by any one element that you want. Now the advantage here is, let's say we have, in case of phased array, if you try to understand the very basic of the phased array, it is very simple. We are applying the time delay. We are applying the time delay to focus the beam at a point. Let's say you want to focus the beam somewhere here. So you are sitting in Srinagar, I am in Chennai. And let's say somebody has to come and meet at a point in Mumbai. And both of us want to reach at the same time. And together there is somebody sitting in Delhi. He also needs to come to Mumbai, and all three of us want to meet at the same time. And the same thing we are trying to do here. We are trying to get beam emanated from all the elements to meet at one point at the same time in phase. So what we will do? We will, because my distance from Mumbai may be larger than the distance from Delhi to Mumbai, or the distance from Srinagar to Mumbai. So that means I will start first, assuming that everywhere the velocity is the same. So I will start first. From Srinagar, you may start slightly later, and the person from Delhi may start the last, in such a way that all of us meet exactly at the same time. So what we need to do is, we need to find out that what is the distance, difference in the distance for all three of us from Mumbai to our places. So wherever the maximum distance is there, that person has to start that much time ahead, and the last one will start that much time at the end. This is exactly what we do in case of phased array. And by doing that, we in the next slide, maybe I'll. So by doing that, let's say we want to focus the beam somewhere here. So the person who is here should start first, and the person who is who is the closest to this should start at the end. So we will delay firing of this element by the time, which is equivalent to basically how much more beam path is here. This beam path can be converted to time of flight by taking the distance divided by velocity. So this will be fired after this much time of firing of this one. And all this will be sequentially fired from this element to this element. You can see this better here in this simulation. Let's say you want to focus the beam at this point. And so the first one to start firing is this. The last one to fire is this one. And by this, you will be able to focus the beam at the point where we want. And beyond that, the beam will again start to diverge. So with this, we will have the advantages, like even in the focus mode, you can get the focusing, even in the contact mode, you can get the focusing of this beam happening inside the material. and that will lead to very high resolution and sensitivity. Then, because you have control on the individual elements, let's say you can fire only the 16 elements first, and maybe the first to 16 elements, then second you fire from second to 17, then the third 3 to 18, and every time you get one A scan signal. It is something like when I was trying to explain the B scan, and we were moving the transducer from one location to the last location. Here, the beam is getting moved electronically from one end to the other, and then we can get so many A scan signals which can be stacked together to generate a B scan image of the sample. So you are able to generate the image B scan without physical movement, simply by electronic scanning. You can manipulate the beam. You can manipulate the beam means you can focus the beam here, 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 or here. So that means like what is done in case when you see for medical scanning, they use phased array. And when they keep at one particular location, electronically the beam is swept. And by doing that, you get focusing happening at different location. And when you see the image looks like something like a diverging beam kind of things, because it is focusing at some location here to here and focusing at all the points, and then you get an image inside instantaneously without the scanning of the transducer. So now, because we are only doing with the delay law, you can have focusing at different place, you can have different angle, beam going at different angles or so. So you have numerous opportunities, and I'll show one possibility where the beam is fired with one element and received with all. Then you have all the information that you can gather from the sample, and then in the post-processing you can do whatever you want depending upon the capabilities that you have to reconstruct the images from the beam. The only disadvantage of the phased array at present is that the cost is of course high, because here you're using one single element, here you're using 128 or 64 elements. So here the cost of the probe may be about 10,000, 5,000 to 10,000 rupees. You can get the probe, some probes, but here the cost may be few lakhs, 4 or 5 lakhs or something, maybe the cost of one transducer. Similarly, the equipment, the instrument that is used is required to be only having one single transmitter receiver channel. So that will be less costly. You can get even in about few lakhs, a couple of lakhs. Whereas in this case, you need to have instrument which has many pulsar receivers, because then only you are able to simultaneously fire different elements with different delay. So that the cost obviously increases with the more and more number of channels that you have in a phased array equipment. So with that, it may cost about the minimum also maybe about some 20 to 30 lakhs or something. And then as you have more and more features, you will have more and more cost increasing. So that's the only, I would say, disadvantage that you have at present in the phased array. And the other little bit of limitation is that because the phased array gives you more option, more flexibility, you can do a lot, but then you need better expertise to understand what exactly is happening with the beam inside the material. But once it is understood and the inspection methodology is well planned, then anybody can just put the probe, because now you're not doing the scanning. So the data is more reliable in this case. So having covered this, now that was what I said was about the transmission part. Now the same thing for the focusing and transmission. Now when the wave is coming back, exactly the same thing can be applied here. Like the wave is let's say there is a defect here. While transmission, we fired this element first, and this one was fired at the end. Then it focused the beam here. After the beam hits here and then gets reflected back, it is coming to the receiver. Then this element will pick up first, and this element will pick up at the end. So we will apply exactly the same time difference what was there in case of firing. In the reception also, exactly the same opposite time difference can be applied, and all the signals can be brought to the same delay, and then after bringing to the same delay, then it can be summed, so that you will get very high amplitude signal here. And because of the averaging effect that is happening also, that also improves the signal to noise ratio in case of phased array. So this is about one possibility, and that is how you can get the, one thing is the sweeping. Another thing I said about the focusing, for example, I'm just showing here is that, let's say if you use immersion transducer. In case of immersion transducer, you should, when you use unfocused probe, it focuses automatically at some depth, which is the near field region. Then this is again with the unfocused, but using 4 megahertz transducer. So the near field is d square 4 lambda. So final lambda, near field gets shifted later. Then this is about the conventional probe. So you can have different lengths, or the probe itself can be concave in immersion. Then you can focus at different depths. But to do this, you will need, even in case of immersion, you will need probes with different lenses, or the different probes itself, to have focusing at different depths. Whereas the same thing can be done by, you take a phased array probe and you focus at more tight focus. You can focus it here. You can give less slope in the delay law. You can focus at larger depth. You can focus it for the larger depth. So basically, you can focus at any depth that you want. And I will show this with some typical examples later. So by selecting different types of delay laws, you can have all elements firing together, focusing at one depth, or a few elements focusing, and then red shows transmission, blue shows reception, and then the beam can be electronically scanned. There is something called plane wave, maybe one example I may show at the end, where all the elements are fired together, and with a different delay laws, it can be fired to generate beam at different angles. So that gives very high amplitude signal, which can be post-processed properly to generate very nice images. And this is the full matrix capture, where one element is fired, all elements are receiving. Then the second element is fired, all elements are receiving. By doing that, you get, let's say, if you have 30 number of elements, so you will get 900 A scan signals, and all those can be processed by having various different types of modes during the imaging to generate defects, which or to generate the images which will have focus at throughout the depth at all the region in your region of interest. And as you develop more and more expertise, you can have your own ways of firing or receiving and developing the images the way you would like the inspection to be done. So just to show, like in the phased array, you can have these are the elements, 4 elements you're using with one particular delay law. So you're trying to send the beam at an angle. So this is a linear delay law. So linear delay law will simply shift the beam at a given angle. Then you can fire here, 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 here. You're translating the number of elements that you're using in individual firing. So it gives you like a B-scan image, and this whole image you get just by putting the transducer at one place in one go. Then you can have, in the previous one I showed, it was a linear delay law, like maximum delay here, minimum delay here, and linearly changing the delay. Whereas you can have superimposed on that focusing effect also. And by doing that, you can focus the beam at a particular depth, and you can do the sweeping as well. So in the previous one, here maybe it's like larger, more divergence, whereas here you should be able to get better divergence also. So with the phased array, you can either do the conventional, you get only the signal, whereas in the phased array, simultaneously you get the A scan signal, you get the B scan image. It can be like either simply giving it an angle in the moving the electronic scanning, or you can do the sector scanning, where all elements can be used and focused at different distances, so at different angles. So this slide shows few different ways by which you, so if you do not apply any delay law, the beam goes and comes back like a plane wave. If you focus at a particular point, you can the beam goes and gets focused here. You can give a delay law, the linear delay law here. So beam goes at an angle. You can superimpose this with this one, and then you can focus the beam and also send at different angles. Then you can have electronic translation along with focusing. So you can have the beam going from here to here so that the entire depth of the weld is covered from one point itself. Now I will show one example where more complex inspection is done, where this we had used for inspection of 250 millimeter thick dissimilar weld, where in center you have the weld, here you have the buttering layer, here you have the ferritic steel, here you have alloy 617. We use 128 element transducer. Phase array transducer use 64 elements to focus the beam simultaneously at different depths. So from the top till bottom, we focus the beam, and electronically it is focusing at all the depth. Then electronically it is moving to the next point, focusing at all the depth. So like this, it focuses the beam at each and every point within the weld, and then by putting the probe at one place itself, we are able to generate the image of the entire thing, whether it is here or here. Everything is generated with very good focus condition. And this is just to show. Then of course we had developed in-house some software for doing better analysis of these images, and then we can generate different images like what I had shown earlier as a B scan image. You can generate the C scan image, and you can also generate the D scan image. D scan image is like a kind of B scan image, gives you the cross section of this side, whereas the D scan gives you the cross section of this, or the projection of the entire thing on the right side. There is a screen on the right side. Let's say if this was a transparent sample and you had given a light source on the left side and a big screen on the right side, so all defects on this will get projected on the right side. And that is what is the kind of image that you are seeing in the D scan. So you can generate D scan, B scan, or the C scan, and then defects in this at different depths. Now, earlier I showed that you have an equation of near field, d square over 4 lambda. And d square over 4 lambda, d is the diameter of a transducer. In case of phased array, when we use a large aperture, when we use 64 element and every element is spaced at about 1 millimeter, it has become something like we have got a probe which is of about 64 millimeter of size. And that large aperture, now if you fit in the equation d square over 4 lambda, so 64 square by 4 into lambda, so that means something like 600 or more, about some 300 or 400 millimeter depth. Up to that depth becomes our near field. So we should be able to focus the beam up to about near field, that is up to about some 200 to 300 millimeter depth. And because of that, we can see that even the defect which was there, we had simulated different. In NDT, always, whenever you try to develop a method for doing inspection, you need to first make reference defects in the sample and then demonstrate that you are able to detect all the critical defects that you expect to be present inside the sample. And so this is for the reference sample. We had made different types of vertical defects, simulating different lack of sidewall fusion. And then there's all defects, you are picking it up here. And then we had even implemented on the real weld. And then you can see that in the real weld, some places we had seen some indications. And these indications were like this narrow gap weld, when you make the bottommost is slightly more narrower here. Here, only one pass fills the entire thing. As you go up from one pass, you may start giving some 2 passes up to some height. Then some 2 or 3 passes may be required to fill up this whole width. And when that is done, the interface at which it is changing, there is some amount of change of the microstructure. The structure is changed, and particularly in case of austenitic material, you get a lot of beam skewing happening, and the scatter also comes because of the grain noise. And that gives that at this levels, we were seeing some indications coming. So it is not just the defect, even the microstructural variation that is there in the weld, that also can be seen, can be brought out very effectively, very clearly in case of when you do with very high sensitivity, sensitive technique. And this is one which I was talking about, the full matrix capture total focusing method, where one element is fired, all elements are receiving. And then we have n number of elements, we get n square number of A-scan signals. And when all the signals are used to focus the beam, you can simultaneously see this is showing up to about 200 millimeter depth or something. The beam is focused at all the points. These are some small side drill holes drilled at different depths in a aluminum sample. And not just this, we are able to even, this is at about 150 millimeter depth, 1 millimeter dia side drill holes, which are spaced with about 1 millimeter gap. All this we are able to, these are all 2 millimeter dia, these are 1 millimeter dia. We are able to very clearly resolve because of using the phased array, the full matrix capture total focusing method. Not just that, when you have all possible signals in n square A-scan data, then you can, depending upon your expertise level and the coding, the software that you can make, you can use different type, because when we send a beam, let's say we send a beam at a particular angle, it goes as a longitudinal wave. But when it goes as a longitudinal wave, depending upon sin I by sin R, the reflected wave will be at, the longitudinal reflected wave will be at the same incident angle. But you will also have another transverse wave going here, which will follow at sin I by sin R is equal to V1 by V2, where V2 is, if you take the shear velocity, so half. So with sin I by sin R is equal to 1 by 2, at that you will have the transverse wave also coming. And that may go at different angle. And all those are picked up by one or the other receiver here. So if you know that what is the thickness and what is the possible location of a defect, you should be able to not just get the single amplitude or a tip diffractor signal or so. It should be possible for you to generate the entire phase of the defect by utilizing different mode converted signals. Then there is something called, maybe I'll go fast now, the TOFD, time of flight diffraction, where diffraction always happens whenever you have a sharp tip. So you have the sound beam coming from the top, you get diffracted signal, from bottom you get diffracted signal. So when you have two probes, first one, the direct signal lateral wave, the second one, diffracted signal from here, then third one, diffracted signal from the bottom, and the fourth one, the signal that goes gets reflected from the bottom. You get four these signals here. And this you can just move on the sample, then you can get a B scan like this, where the top and corresponding to different defects and the bottom reflected signal is seen here. This is top defect, bottom defect, and the bottom signal. And then like whatever focusing is done for synthetic aperture focusing technique, like what is done in case of FMC TFM, something similar to that focusing can be done, applied on the TOFD data. And then you, these are some experimental data for defects which were inclined at different angles. And you're able to very clearly see the top and the bottom tips in all these cases. Then I talked earlier about the guided wave. Guided wave is something where we send this is conventional ultrasonic. You send the beam, gets reflected here. In case of guided wave, you try to send the beam at an angle. Very soon, after multiple reflection because of the mode conversion from longitudinal to shear and all, this entire energy forms one particular mode. And that mode starts traveling inside the material as one single guided wave mode if the wavelength of the signal that we are talking about, or the, is somewhere close to that of the thickness of the sample. So, and the advantage here is that in case of conventional ultrasonics, the beam is diverging like this in the entire volume. So the amplitude that goes decreases drastically. Whereas in case of guided wave, it is guided by the two surfaces. And if it is like a rod or something, it is guided from all the sides. So the total energy is confined in one direction. So that confined energy goes, so it is able to travel at very long distance, even up to a few hundred meters. Like here in this example, people have done for, these are different weld locations. And if the probe is kept at one particular place, zero place, bidirectional, you can see reflection coming from the defects or the welds also at distances from about 20 to 30 meters. Even in our case, we have done for some tubes, steam-generator tubes, where we are able to get reflections from almost the end of about 30 meters or so. And this is very handy in case of like corrosion is happening at the bottom, you put the probe on the top and the wave goes and comes back and you're able to detect this defect. And this, as I showed earlier, that One typical example where we have used is the probe is kept at the bottom, but the wave goes inside like this here. So the wave gets generated here, and it is moving like a packet, which is guided by both sides of the sample. And if there is a defect here, it reflects the sound signal from there. Maybe I can just go to the start. Are you all able to see the simulation?
Yes, sir. Yes, sir. We are able to see it, sir.
Fine. So then such simulations are very much essential when you want to develop a method for doing for a complex structure and the different guided modes or something. So you can see how the signal enters here. How does it go? And when you have a defect, it reflects the signal and it comes back to the same place. So this helped us even in developing like here. If you keep the probes at different places, which location is the best? Like when you keep the probe somewhere here, that is the best location where we are able to send the signal and come back to the same point in the receiver also. Maybe I can just repeat this here. Then this sound wave goes and enters inside and comes back, whereas here it gets scattered from the different boundaries here itself. So this finite element simulation or any other simulation helps us in exactly designing our methodologies and validating also whether we will be able to get signals properly or not. And then, of course, finally we need to do the experiment to see whether we are able to check the signal from there or not. And that also that has to be validated before applying it on the actual component. Then one or two quick other advanced techniques, like in case of ultrasonics, you have EMATs, electromagnetic acoustic transducer. In case of so far the techniques, we discussed that we need coupling because otherwise the sound wave will not enter the material. In case of EMAT, you use, which is full form is electromagnetic acoustic transducer. Here you use Lorentz force principle. So you have a magnet, you have eddy current generated inside the material, and so when you have eddy current generated inside the material and the magnetic field is also there, it generates the force on the material. And that force acts on the electrons or the atoms, and that gives some amount of vibration in the inside the sample. And that vibration, when it is sinusoidal of a particular frequency, it gives you a sine wave. It gives you an ultrasonic wave. And that wave generated inside the material goes and gets reflected. It is again picked up by the reverse of the same principle. And then you can use it for generation and detection of the sound without using a couplant. And that has the advantage that you can use even at high temperature. And for moving sample or something, it can be used for generating for defect detection, thickness measurement, and so on. And now one of the most recent advancements is that the combination of phased array with EMAT. In case of EMAT, the issue is that the sensitivity is poor. We don't get very high sensitivity with the generation with the EMAT. But when you couple the phased array and the EMAT, then we are able to generate higher energy, and the received signal can also be focused in a much better way to improve the sensitivity and the resolution in the material. And that we have seen that. Yeah, and then we are able to even detect defects in the stainless steel weld joint of the required sensitivity for the ID, OD, and all by having the transmitter, receiver, phased array. This is our phased array shear horizontal EMAT probe, where it can be swept at different angles, and then we can get defects at different depths at different locations in the images. Now, it was so far I talked about the big size of defects, but then you can also have micro cracks generated inside the material. Like this was an example for ferritic steel, where you can have, with the creep damage happening, you can see some micro cracks which are generated inside the heat affected zone. And we have used ultrasonic signal to get the backscattered signal, and then like a C-scan image, you can stack different slices and generate the 3D image, which can even give you the idea about the micro cracks which are present. It will not give one strong signal, but it will give you the scattered signal. The grass or the noise level itself will increase, and put all together, you can generate even the 3D image of how exactly these micro cracks are there inside the material. So with this, I would summarize my presentation that there are various advancements in different techniques which are there, and every technique advancement, if one needs to cover, it will be a few hours for each and every technique. So I have just given brief advancements in few techniques like visual eddy current radiography, resistance measurement by XRD or so, but then gone into more detail about the phase story, which is one of the most advanced techniques in ultrasonics, and in phase array also one of the most advanced feature is full matrix capture total focusing method, which briefly I have explained. Then the guided wave is something which we have been using for different application, which is again so-called in one of the advanced method of ultrasonic technique. The EMATs and EMATs combined with the phase array is one of the most advanced technique. Handheld C-scan imaging, which can be used in for doing the C-scan imaging on any component in service. And then for all these cases, mostly to understand when you go to more advanced techniques, more complicated cases, it is always required to get to do some simulation exercise to exactly visualize that what is happening inside, how your wave is going, how your field is interacting with the defect, with the material, with the geometry. What we normally do with the finite element simulation or some semi-analytical software, which is SIVA, and then the results that we get, we try to we develop our own software, and so that we are not limited with whatever is provided with the company or the instrument which is made by some company or some person. But once we have the data and we have expertise, we should be, and if we know how we can visualize the image, what feature of the data that we should extract and process and visualize, then we should be able to use that if only we develop our own software also to do. And this is what we normally do at IZCAR in the non-destructive evaluation division, where the advancements, when we say, is essentially based on the in-depth understanding of the techniques, how exactly the wave is propagating, how the field is interacting with the defects, then detailed simulation that helps us in understanding that, and then we try to develop our own software, many cases the sensors, the system, data acquisition, and then finally generate our own image processing algorithms that helps us in better visualization and interpretation of the data that we get. Thank you very much.
Thank you, sir. On the behalf of NIT Srinagar, I am highly grateful to you for such a fantastic, enlightening lecture on non-destructive testing and evaluation. It's just reflecting your years of dedicated hard work in the area of non-destructive testing. We are really highly grateful to you for this very fantastic lecture. Now the session is open for few questions because we have to leave him at around 4:30.
Hello, sir.
Yeah.
Hello.
Yeah. Hi. Nisar. Yeah.
So while I have a question for simulation studies. While performing simulations, sir, we need to specify some boundary conditions. So
Yes.
in this case, how do we specify the boundary conditions?
Okay. Have you ever done any simulation?
Yes, sir. ANSYS.
What kind of ANSYS? Yeah. So for ANSYS, yeah. So which kind of thing that we are talking about? See, depending upon if we want whether we want a reflection or we don't want a reflection. Like that's the advantage in case of FEM. Depending upon what are you looking for. Like if you are looking for, let's say, at the end and the backward echo reflection or from a defect or something, then you have to give a boundary condition of that the stress-free condition or something there, so that the signal is going and getting reflected totally from there. Whereas if you want to have damping, like we want to mask we don't want to get multiple reflections coming from the side, then we have to give the damping boundary conditions also. Maybe you can even go through some of our papers, like most of our colleagues, when we do the FE simulation, whether in COMSOL or ANSYS. So it is some of the details of the boundary conditions we clearly specify even in the papers it is given. So depending upon what is the, whether you are trying to consider it as a planar defect, whether you are trying to simulate as a boundary between solid and liquid, when we try to take it in case of water immersion or something, or in some cases we don't want the reflection to be coming from some place, we want to hide it. So in those cases we apply some more absorbing boundary conditions, so that slowly as it is wave goes, the continuity is maintained, wave goes inside but gets totally damped. So depending upon different scenario, we may have to use different types of boundary condition that we do.
Thank you, sir.
Any questions, please? Okay, sir, I have a humble request to you.
Yeah.
Is there any possibility for you to arrange a online demonstration or practical session related to phased array, ultrasonics, or any other technique or equipment what you are having and you are comfortable with it on live demonstration? I want our participant should get more motivated into working in this very area, and they get more enlightened how the things are done practically.
Yeah, but I believe that will be difficult right now. See, because being
tomorrow
in
or day after tomorrow.
No, even see, being in atomic energy.
Yes,
we have.
That's why I asked you. That's
yeah, we have a lot of restrictions in that manner. In fact,
yes.
This Google Meet, I cannot have it from office.
Okay.
So
okay.
if we have to have,
I can understand.
If we can have video conference from office, we have to use our own secured network.
Yes.
So that I can access from home as well as from office. And that is why I thought it is better that I stay at home and then finish this year. So in office, particularly in lab, we cannot take the camera or this. Only in the auditorium we can have it. So I believe for this particular moment, it may be difficult for us. Maybe you can request from the other, you have people from other places.
Yes.
Actually. I think they are there is a
they are able to do that. I thought that since you have done a very, I would say, jobs which are very complex, in which you are making use of robots also to take the probes and get the data. It's not an, I would say, easy job. I would say it is a complicated job, and really we appreciate that with such dedication you have done such wonderful work in IG car, I would say. Once again, I thank you for this very presentation. It was really fantastic. It was really fantastic.
Thank you very much. It was my pleasure to interact with you.
Thank you, sir.
Thank you. Have a good day.
Thanks.